Hey people, glad to welcome you all to Code Cohort. In this video, we are going to solve today's daily question from Leetcode. And the question is, construct a binary tree from pre-order and post-order traversal. And the question goes like this. Given two integer arrays, pre-order and post-order, where pre-order is the pre-order traversal of a binary tree and post-order is the post-order traversal of the same tree. Reconstruct and return the binary tree. So as we see that we have been provided with pre-order and post-order traversal of a particular binary tree structure, and the question is expecting us to build the whole tree and return the root of the binary tree, right? Nothing much complex, so it's as simple as that. And there are also two other informations which are need to be noted. So the first information is that all the node values are going to be distinct, and the next information is that if there exist multiple answers, we can always return any of them. Right now, these two informations doesn't seem like making more of a sense. So for now, let's just keep these two information off the table, and let's just circle back to these in a couple of minutes. So yeah, let's discuss the solution. So before discussing the solution, I would like to share a few about this particular problem. This problem is actually a harder problem. Though it has been marked as a medium problem, I don't trust these markers anyways. So today's problem is going to be a harder problem. There are two other predecessor version of the same problem, which are construct binary tree from in-order traversal and pre-order traversal. This is one question. And the other question is from in-order traversal and post-order traversal, construct a binary tree. So these two questions themselves are harder to solve them on the first go. So if you were not able to solve today's question on a single go, please don't be unfair to yourself and start judging yourself. It's completely fine. However, trust me, at the end of today's video, you'll be able to solve all these three questions altogether, right? So yeah, I'll also make sure to pin down the links of these two predecessor versions in today's video's description as well, right? So having said that, let's circle back to today's problem. So yeah, so to solve this problem, there is going to be a prerequisite, which is having a basic knowledge in trees and traversal types of trees. Basically, the above said those. So in order traversal, pre-order traversals, and post-order traversals. So let me just give a quick intro or a short brief of what a pre-order and a post-order traversal actually mean. So let's just take example one, and as we see, they themselves have given the pre-order and post-order traversals. So yeah, there are some set of rules for these kind of traversals. Among those, for pre-order traversal, the rule goes like this. First comes the root value, then comes the values of left subtree, and then comes the values of right subtree. And for post-order traversal, first comes the values of left subtree, followed by the values of right subtree, and then comes the root value itself, right? Now we can just take a moment and then try to cross-check whether these traversals are actually following the pattern or not, right? It will help you understand the pattern much more if you are a beginner. And also do let me know in the comment section if you just want me to create separate videos for all the traversal types of the trees, right? Now, I want you guys to manifest that we have already built a function. That function will be just taking some parameters and it will start building the tree. Okay, so what I'm trying to say is that let's just name the function to be build, and this function is going to take two parameters. These parameters are the starting value and the ending value. I mean, the range of values from a pre-order traversal array. Okay, so what I'm trying to say here is that we have somehow created a function that will take the range of values from the pre-order traversal, and it will build the tree among those values, and it will also return the root of the value after building the tree, right? So right now, just consider that we have already built this function. Forget that how did we figure out this function or not. Let's just circle back for that in a minute. But yeah, right now, just think that we just have already figured out a function that will build the tree and return the true for a specific set of range of values from pre-order traversal, right? So having said this, I also want to ask you guys a question. So do you guys know what is a divide and conquer algorithm means? So basically, it is those kind of algorithms wherein even if you solve multiple questions upon it, you won't be explicitly figuring out that, okay, this is what. a divide and conquer algorithm is. Basically, if you just have solved multiple tree questions, most of the questions you would have solved it using a divide and conquer algorithm only innately, right? It is those kind of an algorithm like greedy and all. Though you have solved multiple problems, you won't be knowing that this is what greedy algorithm actually is, right? So yeah, what are we going to do now is that let's just try to check whether this particular problem can be solved by the divide and conquer algorithm or not. Okay, so let's just take the example one, and now can we just say that the whole tree is comprised of root value and left subtree and right subtree? It is legitimate to say this, right? So yeah, in this whole tree, we can see that root value is going to be 1, and the left subtree is this whole part, and the right subtree is this whole part, right? And now we can also see that this left subtree on its own itself a new tree, right? We can say that, right? And also this right subtree on its own also will make a whole new tree. And if these both are making their own tree, then can we say that these two subtrees are also comprised of root and left subtree and a right subtree, right? So this is also comprised of a root value and a left subtree value and a right subtree value. Now, can we just see the resemblance of divide and conquer algorithm over here? Obviously, there is a bigger picture, and we are actually breaking down the bigger picture into smaller chunks of pictures. And by solving the smaller problems, we are eventually solving the problem of the bigger picture, right? So that is what we are exactly going to do in this particular problem. So yeah, for that, let's just check how exactly can we just use that divide and conquer algorithm in this problem. Let's just take the same pre-order traversal here. And yeah, we know that the pre-order traversal always has the root value at the starting point. Now guys, tell me something. If we just somehow figure out the chunks of values, I mean the subarray that has all the values which are present in the left subtree, and the chunk of the subarray that in which all the values are belonging to the right subtree. If we somehow figure out the range, the starting and ending point of these two ranges, can we just simply pass these ranges to the build function such that this build function will be returning the root, right? This build function will also be returning the root of these left subtree and right subtree. It is basically that if we just send this left subtree, we will be getting this root value. And if we send the root of this right subtree, we'll be getting this root value. And it is just a matter of time that until we give connections from the root value to the left subtree and the right subtree, right? And again, this left subtree, it itself is a recursive problem. This right subtree, it itself is a recursive problem, right? So for now, what we have to figure out is that we know that the first value is always going to be the root value, and right now we should have to figure out the chunk of values that belong in which all the values are belonging to left subtree, and the chunk of values in which all the values are belonging to the right subtree. How exactly do we figure this out? Now tell me guys, is only pre-order traversal enough to figure out this information? So here, if you guys see in this example, we have been given with a proper binary tree, like a complete binary tree. That is why, leaving out the root node, we are having equal number of nodes in the left subtree and in the right subtree. But what if there are extra values, additional values in the left subtree, like this, something like this, right? In that way, the left subtree will be having extra values and the right subtree will be having lesser values. In that case, we won't be able to divide it into half and check that and say that all the left side half are having the values which are present in left subtree, and the next half are present in the right subtree. We cannot actually do that. So this is where post-order traversal comes into existence. Let's see how post-order traversal is actually going to help us, right? So as we have added post-order traversal as well, let's just make a bit of a tweak in the build function. Previously, we just only had start and end, right? But it was not seeming to be working. That is why we just have added post-order traversal as well. So right now we should have to have four values: start and end position from pre-order, and start and end position from post-order, right? So initially the starting and ending points will be at the two farther ends, because we need the root of the whole arrays, right? So here S1 and E1 will be there, and here S2 and E2 will be situated. Yeah. Now let's see how to progress from here. So here we know that the root of the, this is going to be the pre-order traversal, so that the first point will always be the root node, right? Now, our conquest is just to figure out the size of the left subtree. If we just somehow figure out the size of the left subtree, then we will be figuring out the size of the right subtree as well, because the remaining elements will be for sure the right subtree elements, right? So let's see how to figure that out. Now, we don't know the ending point of the left subtree yet, but we are sure with the starting point of the left subtree, because if this is going to be the root of the whole tree, then obviously left subtree will be starting right after the root of the whole tree, right? And then if this is going to be the starting of the left subtree, we can also say that this is going to be the root of the left subtree, right? Because this left subtree will also be following the pre-order traversal, right? So yeah, right now we just have figured out the root of the left subtree. Now, what are we going to do is that we are going to find the position of this particular root in the post order traversal. So that is situated over here, right? So this is the root of the left subtree of the whole tree. Now, how to figure out the size of the left subtree? Can I say that starting from the S2 position till the root position will be the size of the whole left subtree? How are we just saying this? Because this is going to be post order traversal. If root is coming here, before the root comes the LST and RST. Do you remember that? This is the rule of post-order traversal. LST comes first, then comes RST, and then comes root. If root itself has been located over here and the starting position is given up front to us, then the length of this window is indeed the size of the left subtree, right? So here it is going to be 3, right? All these pointer manipulation and all, just leave it behind. I'll just teach you guys that while writing the code. So right now, just understand the concept only, such that we don't have anything left out before moving to the code part, right? Although I'm just not going to do the whole dry run, but yeah, with what I'm going to explain, you'll be pretty much getting the concept behind this problem, right? So yeah, for now, we have figured out the size as 3. Excuse me. So here we also can figure out the size of the left subtree, because we have figured out from here. So the starting point, new starting point will be here. The new ending point will be here to be passed to the build function, right? And this is for the left subtree, and the remaining elements will be definitely of our subtree, right subtrees, right? Then for the right subtrees, this is going to be the new starting point, and this is going to be the new ending point. Cool. And yeah, so now we are having ready-made values for the recursive calls in pre-order traversal. In pre-order traversal, we have the starting and ending points of left subtree and right subtree. Now let's just make the same for post-order traversal as well, because by using post-order traversal only, we'll be able to find the left subtree size. So we have to parallelly send all the 4 values. That is why we should have to make 2 values ready-made along with each other. Right? Yeah, we now have figured out, we already have figured out the size of the left subtree. So yeah, this is going to be the new starting point, and this is going to be the new ending point for the left subtree in post order traversal. And we always know that in post order traversal, the root value of the whole tree will always be at the end position, because of this rule, right? LST, RST, and comes the root. So root value will be always at the right side. So if this is going to be the root value and this chunk is going to be the left subtree, obviously the left out will be of the right subtree, right? So this is going to be the starting point, and this is going to be the ending point of right subtree. Now yeah, we are done with the left subtree as well. We are done with the right subtree as well for post order traversal. Right? Now we can just call a recursive function by having all these information, right? And for these individual chunks as well, let's say, see, this is the left subtree, and this is going to be the equivalent left subtree from post order traversal. Just what we have done for the whole subtree, if we just keep on repeating the whole action for these subtrees as well, can we just does it sound like divide and conquer, what we have just discussed over here, right? We are just breaking down the whole problem into smaller chunks of problems, and finally when the edge case is getting hit, we'll be just returning the tree node with which we'll be building the solution for the whole tree. Okay, so talking of speaking about the edge cases, here there are two edge cases. I'll talk about one edge case over here now only, and I'll talk about the second edge case while we are writing the code. Okay. So the first edge case, it is not the edge case. We can also say that it has a base case, right? So can I say that whenever the length of the window is going to be 1, so something like this. So if start 1 is going to be equal to end 1, whenever the length of the window is going to be 1, can we say that we cannot pursue more than that, right? Let's say we just have reached this value, the leaf nodes. Do we have any more subtrees? Here I just have drawn them for examples, but in this example ideally there are no further children for these nodes, right? In that case s1 will be equal to s2, right? So in that case we won't be moving further. So this is all about the whole concept. Now let's just quickly see the code part, and one edge case is missing. I'll be just also talking about that in the code part. Moving forward, let's just quickly see the two information which are given in the question, right? The first information is that all the values are going to be distinct. Now guys, tell me, do you understand the significance behind all the values being distinct? Because you just have pointed the root value of the left subtree, and while you are searching for the root value in pre-order traversal, post-order traversal, what if we just find multiple values which are 2? Would it not cause an ambiguity, right? So that is why in all these kinds of problems, like construct binary tree from either in order or pre-order, in order or post order, or pre-order or post order, you will be always promised that all the values are going to be distinct, right? So that is one thing. And let's go to the next information. In order to make you understand the next information, let me just quickly draw two small trees. Okay, so the trees will be like this: 1, 2, 3, and 4. So the other tree will be just this, but with the left side subtree, 3 and 4. Now, can you guys quickly figure out the uh, pre-order and post-order traversal for this? So what is going to be the pre-order traversal for this, the first tree? So the pre-order traversal is going to be 1, 2, 3, and 4. And what about the post-order traversal? The post-order traversal is going to be 3, 4, 2, and 1. Now let's do the same for this pre-order, post-order. So the pre-order is going to be here 1, 2, 3, and 4. Also here it is going to be 3, 4, 2, and 1. Now, if you guys see, the pre-order and post-order traversal are actually similar for these both structures, right? However, the structure of these two are not similar. Pre-order and post-order traversals are similar, right? So what does this signify? This signifies that these pre-order and post-order traversals doesn't define the actual structure of a tree, but these define the way we just hop from one node to another node. So that is why the question is saying that even though there are multiple answers possible, just return any one of them, right? Now there is a question: which kind of answer do you think our solution will be providing? Take a minute and guess. I would say that it will provide this kind of answers. It will always prioritize the left subtree instead of prioritizing the right subtree. Because let's say this is the root value. Now this is the root value of the left subtree. But ideally this has to be the root value of right subtree. But what are we actually figuring this out? We are figuring this as the root of the left subtree, right? So that is why we will be always prioritizing the left subtree over the right subtree, right? And that is not wrong at all. We actually don't care, because it doesn't define the structure of the tree. However, it does define the way we just traverse from one node to another node. So that is all about the two information which are given in the question. And let's just quickly see the time complexity as well. So yeah, what is going to be the time complexity, guys? So here, let's say that once we plot out the root of the left subtree, we will be searching for it in the post order traversal, right? But if we somehow use a hash map and store all the positions from the post order traversal up front, then we will be getting this information in O of 1, right? We don't have to do a linear search over here, right? So again, storing it in the hash map is going to be of O of n, and then plus, then for traversing the tree. So see, once we just figure out the size of the left subtree, then it is just a matter of fact that we will be doing a LST traversal and an RST traversal. It is as simple as root LST and then RST. It is a O of n traversal because we will be meeting each and every node only once. So that will also contribute an O of n traversal. So time complexity will be approximately O of n. So now what about the space complexity? So space complexity, obviously we are using a hash map. So it is O of n, and the stack, recursive stack, that will be of, if there are n nodes here, then the height of the tree will be log n, right? So O of n plus log n. Forgive my handwriting. Now space complexity will be approximately equal to O of n. So with that being said, let's just quickly dive into the code. All right, let's just quickly see the code now. So why did I choose Java? Because I personally feel that people who follow other languages as well will be able to understand Java, because Java doesn't have any weird syntaxes like Python does have, right? So that is the only reason, no other reasons. So yeah, the code has two parts. The first part is to store all the positions in a map. So let's just do that. So integer map global variable, and let's just initialize inside the function. It is simply a map. So now let's just so n is going to be the length of pre-order or post-order, whatever it is, because they both are of the same length. So now let's just traverse which I is equal to 0, I less than n, and I plus plus. Now in map we are just going to put the position of a particular value. The post order value at ith index is going to be staying at ith index. So this is what we are going to store at the hash map. Now finally we are just going to return the return value of the build function. This is what is the function that we have manifested, and what are the values that this function is going to take. So this function is going to take start 1, end 1, start 2, and end 2 values, which we have already discussed as well. So here, and also we have to send the pre-order and post-order arrays. That is pretty much basic. And yeah, s1 instead of s1, what should we have to send? We should have to send 0 to n minus 1, because this is the starting recursive call, such that we should have to include all the elements in the array, right? So that is pretty much done. That is pretty much with the first part of the code. Now yeah, let's move on to the second part of the code, which is the build function. So tree node build, so integer array pre-order, integer array post order, then s1, then s2, sorry, e2, e1, s2 followed by e2, right? Now yeah, so there are two edge cases. We just have discussed one, so let me just write that edge case. So if s1 is going to be equal to e1, which means that we have reached the leaf node and there is no way for us to progress any more further than that. So we can just and also the length of the window is just 1. So if the length of the window is just 1, why don't we just create a tree node for that window and send the result. So pre-order of s1. So if you guys see that these s1 and s1 and e1 are the indices which are belonging to pre-order, right? See, we don't have to see if s1 and e1 reaches on the same particular position, then s2 and e2 also would have reached, right? So that is why we are just ignoring s2 and e2. Checking s1 and e1 itself is more than enough, because these both are moving parallel to each other in all the recursive calls, right? As these are indices of pre-order, so we are using pre-order to create the value. Cool. Yeah, and again s1 and e1 are equal, so that is why either of these will work to index out of the actual value from the pre-order traversal. Okay, there is going to be another another edge case 2, which I'll be talking at the end. Okay, now let's create the root value. So the root value is going to be tree node of, guess guys, guess what? So it is going to be the first value from the pre-order traversal, which we have already discussed, right? So the root value is done. Now we should have to create the LST. We have to create LST and we have to create RST, right? Let's say we right now have LST and RST. Then what should we have to do? Just root dot left is going to be lst, and then root dot right is going to be rst, and then finally we are going to return the root value, right? Now let's just come back to the calculation. So in order to find rst, we should have to find lst, right? Because with which only we will be developing the intuition to find the window size and all. So in order to find the left subtree first, we should have to figure out what is the size of the left subtree, right? How to figure out the size of the left subtree here. So for that, we should have to have the position of the value from the map, right? Position of the root value of the left subtree from the post order traversal, which we are actually storing, which we have already stored in the hash map. So let's just get that. So root position lst root position is equal to map dot get of pre-order of s1 plus 1, because see, if s1 is going to be the index of the root node in pre-order traversal, then the very next node then the very next index will be having the root of the lst, right, which also we have discussed in the explanation. Cool. Now this will be getting us the position. Now getting the length is just a matter of using the math formula. So let's just name it as lst size is equal to lst root position minus the starting 2 position plus 1, right? This starting 2, we have to use starting 2 because s2 position is used because we are indexing out the window length from post order traversal, right? That is why s2. Be careful while using these pointers and all. So yeah, what are we doing here? It is just a simple math formula, b minus a plus 1. So here b is going to be the root position and a is going to be the starting point of that window, and then plus 1, right? So yeah, we just have figured out this value. Now let's try to figure out the left side, left subtree. Cool. Now what is the first value? First value is pre-order. The second parameter is post order. Now what will be the s1? So S1 is going to be the root value, right? So the root value is going to be S1. So the starting point of the LST is always going to be one step ahead of the root value. So it is sorted. Now coming to the end one. So what is going to be the end size? Sorry, end point of the left side, left subtree. It is obviously S1 plus LST size. We have figured out the size of the LST. So S1 plus LST size will be the end point of the left subtree. Cool. Now, what is going to be the left subtree starting point and ending point from post order traversal? So this starting point is already going to be the starting point because we just have I mean the starting point 2 is going to be the same because with which only we just have calculated the LST size, right? The starting point is going to be the same, and what is going to be the ending point? It is obviously the same, right? The LST root position is going to be the ending point, root position, right? So this is done. S2 is done, LST root position is done. Now coming back to RST. For RST, let's just do the same thing. Build function. So first parameter pre-order, second parameter post-order. Then what is going to be the starting point of the right subtree for pre-order traversal? What is going to be the starting point? See, if this is going to be the ending point of a left subtree, then obviously one step ahead of this will be the starting point of the right subtree, right? So let's just do this LST size plus 1 because it is all left subtree is going to be the starting of the right subtree is always going to be one step ahead of the ending point of the left subtree. Cool. Now what is going to be the end point? End point is going to be obviously the end point of the array only, or the window only, right? So let's just put E1 only because all the remaining elements are going to be situated in right subtree. So the end point is the utmost end point. So we just put the same end point over here. Now, what is going to be the starting point of RST in post order traversal? Now we know that the starting point of RST in post order traversal is S2 and ending point is root position. Now, if ending point is root position, then it is just LST, RST, and then root, right? So after LST, or I mean, obviously RST comes. So here, can I say that LST root position plus 1, like pretty much similar to this. So end of the LST plus RST plus 1, right? And then what is going to be the end point? End to minus 1, because at the last position root value is going to be there. So we should have to exclude the root value, and we should have to take the window which is left side to the root value. And that's it. And that's it. Let's see whether it runs or not. It runs perfectly fine, but it won't get submitted because we did not take care of the edge case, the second edge case. Yeah, so it is giving some index out of bounds. So let's just code the second edge case as well. So here, if S1 is going to be greater than E1, right? In that case, we just have to return null. Right now, it will be just working fine, I suppose. Yeah, it is fine. Now, if you guys see that it is giving us 53% beats, but ideally it should give 100%. But let's just check what is this 100% beats guy doing, which we are not doing. Right. See, he is also pretty much doing the same thing that we are doing, but the only thing which he is doing differently is that he is not using any hash map to pre-calculate the positions. He is just doing it on the go, right? And this is giving him better results because the constraints of this problem are very less. It is only 30, right? So when the constraint is very less, on the go calculation and all will be O of 1 only, because 30 itself is a constant. So on the go calculation will be O of 1. But for us, it is just taking additional overhead. Again, you can also try to do it on the go. It is not that of a big deal. But yeah, when the constraints are going to be bigger, then obviously our solution is going to be standing on the top, right? So let's just quickly see the explanation for this edge case, like when does it exactly happen, and then let's just wrap up the video. All right, guys, let's understand the second edge case and when does it happen by using this shorter example. So yeah, and the pre-order and post-order traversal will be as follows. And here, as you see, the length is going to be just 2. Okay, so let's just dive into the recursion. So here at starting 1, ending 1, start 2, end 2 will be at the farthest ends, right? Towards the left side and towards the right side. Cool. Now, what we will be doing, we'll be just creating a root node here, right? And we'll be figuring out the length of the left subtree. So the left subtree's head is here, and it is also here at the post-order traversal, and we see that the starting and the root position is at the same position, which means the size is going to be 1. If the size is actually 1, then how our left side call will be resembling like? So S1, E1, S2, E2. So here, yeah, we now have figured out the size of the left subtree, and the starting of the left subtree will always be S1 plus 1, which is 0 plus 1, 1, and end will be starting position plus the size of the uh, LST, which is again 0 plus 1, right? And now what will be S2? S2 is going to be the very next position. Sorry, S2 is going to be the same position, and E2 is also going to be at the same position, because the length of the window is single, right? So here also it is going to be 0 and 0. Now, can you just see that we have hit the first edge case where S1 is equal to end 1. And also, do you notice that here S2 is also going to be equal to end 2. That is why I just have mentioned previously that these pointers are going to be moving parallel in the sense they will be moving in an ambiguous way, but while they just end in a particular way, they'll be ending, the condition of those two will be same while they both are ending, right? That is why it is more than enough to just check any one of the two pointers, right? So now let's come to the right subtree. Here is the ambiguity which is going to happen. So S2 is here, N2 is here, and what is going to be the start position? The start position is going to be the ending position of left subtree plus 1. But here S1 will be going to the end, like it'll be going outside of the bounds, right? So here what will happen? So 1, so 1 is the last position, 1 plus 1, which is going to be 2. Here it is going to be 2. However, end 1 is going to be staying the same, so it is 1 only. Now can you just see that S1 is actually greater than E1? And in the what is going to be the case of S2 and E2? Here the ending position is here. Ending position is here means the starting position of RST will be starting plus 1, right? Plus 1 of the ending position, which is again 0 plus 1, 1. Now here E2 is considered here. this particular position is considered as the root value. So the correct value should be e2 minus 1, which is again 1. Sorry, which is 1 minus 1, which is 0. Now here also, can you just see s2 is actually greater than e1, e2. And now at this position, what are we going to do? We simply have to return null, right? Because this is not a valid function call. So for all the invalid function calls, if we just return null, the flow wouldn't break at all. So yeah, that's it, guys. That's all for this video. I hope you have gained proper information to solve this problem. And I guess that the video is getting longer, so I couldn't give you proper intuition for those two predecessor version on as well. But yeah, however, if you just want me to create separate videos for those two predecessor versions, or even if you want me to create any videos for your suggested topics, please do let me know in the comment section. So yeah, I guess that's it for today's videos. Cool, guys. Until then, it is Arvind signing off.